Hello all, welcome back to the part B of lecture series 8. In the previous video, we discussed how to use simple linear regression model technique to model time series data. In that case, we consider two objectives. One was to forecast a long trend or long-term forecast using modeling the trend and seasonality, and then short-term forecast using autoregressive model. In this video, we are going to see how those models were actually fitted with the air passenger data. So let me go and start the R, and I will share this code on the Swarm portal in the NPTEL portal. So first line here is it's just remove the environment, any variable are there, so it will just remove the environment, clean the environment. If you just run air passengers data, it is available in the base data set, then it will just plot the air passenger data set. The data set is over the time period from early 1950s to 1960s, and here is the air passenger values. In fact, if you just do question mark air passengers, here it is talking about the classic Box-Jenkins airline dataset, monthly total of international air passengers between 1949 and 1960. So here is the data, and if you just run this, in fact this data, just copy and paste it and just run it, you can see the entire data set. It's a small data set, but you can see the entire data set, Jan, February, March, April, May up to December, and then each row sort of or a particular year. So it's a nice data set which you can see, and now we are going to model it. Now from here I'm going to extract the time. So TM, if I just plot the TM, you can see that Jan, Feb, March, every month the time is being converted into a numerical value. So we call it TM, and N is the length of the TM. So N is, so about 144 values are there. So we consider from 1949 to 1956, that is 8 years of data as training data. So 12 into 8, every month we have 12 months of data over 8 years. So we are going to use 96 data points out of the 144 data points as training data. So I'm defining my training data as data frame, where y equal to air passengers from 1h to m, and tm stands for time. So if I just now write head of data, header data train, so you can see that this is the data on the first few days of data, few months of data. Okay, now we are going to consider from 1957 to 1960, that is 57, 58, 59 and 64 years of data as testing data. So about 2/3 data we are going to use for training, and 1/3 data we are going to use it for testing. Okay, so here is we are running it as a testing. So here is the test data set. It is a train data set, and this is the test data set. Okay, now this piece of line is going to create just the frame of the plot. I'm going to create some visualization. Let's, as our discussion, you know that visualization is sometimes helps to understand it helps us to understand the data and what kind of model can be used. So here I'm just creating a framework. Just on the x-axis I'm saying don't plot anything, just x-axis will have the times and y-axis will have the dates. Then from the time train you plot the data with purple color, and then from the test dataset you plot the data with the blue color, and this is the red line that we draw. So this part of the data we are going to use as a train data, and this part of the data we are going to use as a test data. So the first model we are going to fit is y equal to a plus b time plus error. Okay, now we just fit the data summary, and this is the summary. So this is what we have seen it in our presentation also. If we just, so this is what we have seen, and adjusted R square is 81.6%. So that means 81.6% of the variability in the air passenger data can be simply explained by the simple linear trend. Now from that I can compute the fitted values, and I just define it as a time series and plot the line. So this is the fitted values, and from there from the fit trend we just extract the residuals as frequencies as time series data and plot them, and these are the residuals. You can see this is the residuals, and we plot a 0 at 0, so some will be negative, some will be positive, and we can see that residuals have the seasonality. Now we plot 2 pi omega by 2 pi. Now we don't need to define it as a 12 because we have defined it as a time series data, and here frequency is already defined as 12. So that's why I don't need to divide it by 12. So because it is already being defined as a frequency of 12. So data set is residuals, and now in the data set train you see I have extracted the residuals. Okay, extracted the residuals and fit the residuals as a function of sine omega time plus cos omega time. Okay, now this is the model what we want to fit. Residual as a function of a plus b times sine omega t plus c times cos omega t plus error. This is the model we want to fit. So we fit this model. Sorry, we need to run this guy. Yeah. Now you can see that, let me just enlarge this thing. So now you can see that this sine cosine is trying to capture the seasonality, annual seasonality of the data, but it misses the highs and lows of the data. Now then we fit a second order residual Fourier transform, and we plot this, and now you can see that this red curve is actually trying to capture this local seasonality. this local seasonality is trying to be captured by the second term Fourier. So now if we fit a trend and seasonality together, what we are getting is, and then almost, so that the time that the sine, cosine, everything is kind of extremely significant, and adjusted R square is 0.942, so 94% of the variability get explained by the model. And then we plot the model and then fit hat. So we can, in the in sample, the fitting is quite good. And let's do the out of the sample prediction. This is out of the sample prediction. Out of the sample prediction. So we do that. And then we can see that it's definitely missing the, if you just let me just, so these reds and these greens are out of the sample forecast, and clearly it is missing the highs of the max, the peak seasons. So we take the log transformation, fit trend and seasonality with log transformation, and then on that we run a stepwise selection transformation and run stepwise variable selection to choose best engineered feature to capture the seasonality. Okay, so let me just run this. So you can see sine, cos. Now all the cos terms of fourth and fifth order cos terms are being dropped. Okay, so and sine 6 and cos 6 are also being dropped. So now if we draw the plot, so this is in sample fitting, which is pretty much picking up the entire model, entire data, nicely doing, and this is out of the sample forecasting. The green is out of the sample forecasting. It is slightly actually overestimating now. So anyway, so this was the modeling, long-term modeling. Remember that actually why I am calling it long-term modeling, I am doing the entire forecast just standing here. Entire green forecast is being done while you standing in the 1957. Right, remember that. So it is, I am doing the entire 4-year forecast while standing in the 1957, and it is doing reasonably good. You can see it is, yes, of course, farther away the error will be higher, but at least the first year and second year it has done pretty decent job, and it has picked up the nature of the trend and seasonality to a great extent. Now we are going to do the short-term forecasting. Short-term forecasting with autoregressive model. Okay, so here is the data. Simple basic data that we have. So basic time and the y. Okay, and then we are taking the lag ones. Just created the lag ones. So y, so 12 is being just placed here. So if it is 112 on the February of 1949, the lag is 112, it is being kept here. If 132 is the value for the March, then 112.18 is the lagged value, and that is being kept here. Similarly, 132 is being kept here. So that's how you create the lag variable. Okay. Once you create the lag variable, now you plot the lag variable versus the actual variable. So now you can see that this is the lag variable versus this is the original variable, and there. Okay. Now I'm going to create a log difference of the values, and then so if you now you see these are the delta y log differences and then lag of the log differences. I've created lag of the log differences. Again, I am going to take the first 8 years of data as training data and next 4 years of data as the test data. Now I'm going to plot this yt versus yt minus 1. So you can see this, sort of a points. Okay. And then also this plot, you can see this is a delta log yt minus 1 versus delta log yt, and you can see that there is a sort of a hole in the data, right? And this hole represents the seasonality. Okay, so question is there a second hole there, or is it just why this case is so tense? So this is something the topological data analysis people do consider, why it is happening, why the way it is happening. This topology, what is the topology of the data? All right, so now I'm going to fit this model in delta y as a function of delta log y, lag of y, then summary. Interestingly, you see they're not very really not very significant. None of them are really adjusted R-square, not very high. So if I just run the BP test, Bush-Pagan test, they are not also homogeneous. So probably I will not use this model at delta y level. So if you just model fit this model simply y versus log y as a function of lag y, simple autoregressive model, so at least immediately what we are seeing that it is very strong model with adjusted R-square 0.89, and we ran a Bush-Pagan test. The Bush-Pagan test still rejects the homogeneity, and if we fit this, you can clearly see at the beginning it was much more dense, but as it increases, the residual increases with that. It's like a fan kind of behavior. So clearly it's not homogeneous, and a line plot also sort of initially it is the residuals, these are the residuals much less, but the residuals much higher at the end points. So if we just fit this guys, but still if you fit this guys, they're doing pretty good job in terms of prediction and in terms of out of the sample prediction. So we will stop here. And next video we will move to the Granger causality test, and what is Granger causality and how it is going to play a big role in the causal inference, and how simple linear regression model that we discussing in this can be used to develop some Granger causal model, and Granger can be used in defining Granger causal inference. Thank you very much. See you in the next video. See you soon. Take care. Bye.